Audio check. 1, 2, 3. Okay, sounds like I'm live. Ladies and gentlemen, welcome to the stream of the Discourager of Hesitancy. We are building a game with no game engine. The game is done. And we're to the point of doing some space optimizations. The last 2 days, we spent optimizing our audio usage. We were using dual channel 16-bit PCM at 44.1 kilohertz sample rate. And that's actually where most of our executable size is coming from and where most of our compile time is coming from. We take 111 megabytes of audio data and embed that directly into our code files, and it's embedded into our executable. So we have a way to shrink that down by a quarter. Hey, L-Sci Kangaroo, how you doing? How you doing? So we've got that to where we can compress our audio by a factor of 4, well, by 25% to 25% of the original size. But some of the sound files don't sound good doing that. I'm all right. Good. Glad to hear it. Bit of a delay today. Some days the lag is better than others, but that's the way it goes. So here on our journal, we have what we were doing before we started this little process. So 4.165 million lines of embedded data. Our total size of memory is 111 megabytes of audio. And we can shrink that down quite a bit, but some of the sounds don't sound good with the MULA encoding. So what we're going to do today, we can now embed either one. Yesterday that was the thing. We want to embed and play back either PCM or MULA, and we want to play either mono or stereo, and choose on a per sound basis. It turns out that all of our sounds can be played back with mono with no real problems, because our audio is so similar between the left and right channels. Most of our audio, I think, can be played with MULA, but there's a few that we need to go PCM, and so those will take up a bit more space, but that's all done. So, actually, I remember, yeah, there's another thing we did. So we're going to pull this into today's tasks. 18 tasks and notes. So after hours, I went through every sound file and I looked to see if there was a lot of trailing zeros or leading zeros, and I trimmed those off. And I'll be curious to measure how much space that's going to save us. So measure improvement with trimmed zeros from audio. Nobody needed to watch me open each audio file in Audacity and scroll left and right and delete and play back and make sure it sounded okay. That's just not interesting project work. Oh, I've already drunk my mate for the morning. Okay, we need to get some more waters eventually. So that's 2 things we're going to do. Those shouldn't take long. Question mark. Everything always takes longer than you expect. Which brings us to our to-do list. We did that. Oops. Yes, we did. I have been slowly working on the art for these, but it's not a fast process for me. Then we'll start on this one. Then probably these ones. So that's our plan for the day. We'll see how far we get. So here we go. We're going to measure how much memory we saved by trimming zeros from our audio. If I go to the last time we embedded our audio, we have a lot of good data here, which we're going to put in our scratch buffer. And then we're going to delete all the left-right variants. So search for left, right, delete. We don't need the output either. Okay. Our file was this. We had this much sample data, and we kind of don't care about the compressed size right now. Not for this comparison. So we're just going to delete compressed off the end of each of these lines. We also don't care about the time. So I'm going to search for the arroba, delete it. Delete all those. We're just, yeah, conditioning our data here. Let's see here. Sound, file size, data size. That's mostly what we need, I think. All right. What we're going to do is we're going to delete the leading hyphen, search for colon. We're going to delete all of that. Okay. There. That's the data we have. Hey, G Finelli. Doing good, doing good. How is your stuff going? How's your game engine? How's everybody's projects doing? Okay, so we have a record of how big our files were and how big the audio data was. So if we come in here and we do /, let's see here, embed as, we run this again. Well, it's going, lol. Ah, sounds like you're at the fun part of the project. So we're just going to copy all of this data into our scratch buffer. We do that and that. Still working on textures, but the last refactor made things a bit easier. Good, good. Yeah, once you can render a texture, I mean that's 90% of the battle right there. Oh, oops. Don't want to do that. Okay. Let's do this. Start over. Pipe. Pipe. Delete. Delete. Darn. Okay. Right. Delete. Pipe. Search for colon. Pipe. Forward word. There we go. Okay, so we get all these. All we really want, let's see. looking into basic atlas, so passing UV and having an animator, struct, and system. Nice, nice. A sprite atlas or a texture atlas. Good stuff. Ours is it's not everything I hoped it would be, but for building it myself, I don't think it turned out too bad. So this thing, I'm gonna search backwards for that. Okay. There we go. All right. There we go. I think we've got all of our data put in a way that we can work with. Look at temp or buffer and put all in. There we go. Okay, now it looks like something got messed up. Click. Oh. I think this click was supposed to go there. And this click stays there. I think that's probably what was intended. Okay. So all we really have to do, let's see here, there's a way to do this. That regex or pattern matching thing you are doing is satisfying. Thanks. It's Emacs. We can program macros. So I hit a key, hit F3, and it starts recording all of my keyboard shortcuts. And as long as I think very carefully about what I'm typing, I can apply it over and over again. So that's what the what that is. Keyboard macros, super powerful tool. In fact, it's because of that that one of the best things I've heard is Emacs isn't a text editor, it's an interactive environment for writing text editing programs, which is what you just saw me do. I wrote a program that said, find the first pipe, find the second pipe, find the text in between, copy that, search backwards for the word, then paste these things. And so it's just a program that I wrote, but it doesn't look like it. It's super slick once you start thinking of it that way. Let's see, text your your atlas won't be hard. Already have something in mind. Good. No, and you're building it yourself, which is great. Then you'll learn how it works. Then in the future, if you run into somebody else's text or atlas, you'll be like, okay, I know what this is doing, and I would have made different choices, but at least I understand what the choices were. So very nice. Especially now that they've refactored the code. Yep. Refactors are good. Oh, show, nice. Yeah. So Emacs, I still like Emacs. So I think we mostly just care about data size. I don't think the file size matters at all. So why don't we, there's a way to remove a column. There it is. And this column. There we go. Old data size, new data size. There's a way to add a column. There it is. Size difference. Now, do I remember? I don't remember how to enter in the equation. Let's see here. Emacs, org mode, row equation. There's a simple keyboard shortcut for this. Just have to remember what it is. Column formula. C question mark. Oh, C question mark. Oh, Control C bracket. Interesting. Print formula, empty field, now type colon equals. I think that's what I need. Colon equals. So in theory, I can do this. Control C question mark. This is column 2. So I can say column 2 minus column 3. There we go. And we saved that many bytes. While still in the row, hit Control C minus. Control C minus. Oops, nope. There's a way to apply a column. All the fields in the column by applying Control U, Control C star. Control U, Control C star. Control C, Control C. There's a way to do this. Org mode, apply column equation. Control C equals. I don't think that's what I want. Control C equals. UUC equals. Oh, got it. There's a way to do this. Once you get this value filter, you can Control U, Control C star. Nuts. Add that thing back. Okay, so Control C equals, no. Only difference is prefixed by equals instead of, okay, so if I come over here, we're just gonna start over. Equals, $, I don't remember all the rules for this, $3. And then we say Control C equals. Control C, Control C. There we go. Phew! Okay, yeah, apparently I'm a little rusty here. If I use this more often, total, and all we really want is a cell equation, which is the sum from here. So there's a way to do this. V sum. Oh, come on. Org mode V sum. I know there's a way to do this. Field and range formulas. Like that. So colon equals v sum from 2 to 3. There we go. So what this equation means here, so 32, 4 says sum up from the second line to the third line. So there we go. We can take that and we can say divide 10518. Actually, let me just do that here. Divided by 1024 times 1024, I think. We saved about a megabyte. Look at us go. All right, so I saved about a megabyte of raw audio data. That's not much, but it adds up. Also, hey, yes, audio file size, thank you. You have a good stream and come on back. Let's see here. My code now is basically using resources as global things for systems. Yes. So systems have some resources to deal with rendering, batching, and setting those values. Good. Global is bad, but not in this case, as they are indeed global. Yep. So things like textures and yeah, I have a few of those sorts of things that are definitely globally treated. I wrap them up inside of a namespace or a pure static class, just so that I don't have naming collisions. But yeah, no, global is not your enemy. It's uncontrolled, unthought of global state. That's what gets you. Not thinking through your problem. So this one equals v sum at 11, 1, 2 to 3. We'll just go ahead and keep that. So yeah, it's about a megabyte. It's in journal. Saved length equals about 1 megabyte of space. The other reason I wanted to trim that sound data is when we play a sound, we wait until it's done. So if a third of the sound is zeros and there's no audio coming out, I still can't mark that sound as done. So this makes all of the sounds sound a little snappier. They're gonna start up a little quicker and they're gonna terminate a little earlier so that the next sound can start playing. A lot of times we're waiting for a sound to finish to tell us that a thing is done. And so this will actually tell us when the sound is finished, not when it's just done playing, because we've trimmed all that trailing zeros. So that's going to make this audio sound a little bit snappier in some cases. So that's good to know. We saved about a megabyte of space. I guess I can just go in the notes here for today's tasks. Trimming zeros in audio saved about a megabyte of space. Cool. All right, next task. Let's see, in this case, it might be too much, but it makes sense in my head. I have a sprite renderer resource that will be used by its system to send information to it. Yep. So far that makes sense. And yep. Okay. All right, so we need to do some per sound testing. So we're going to go into our Sandbox. We have this thing we called audio, sound. We don't need to worry about those. Init sound time test. I don't want that one. I thought we had like a something like that. Init sounds test. And update sounds test. This actually number keys as piano notes. Okay, so I like the volume being up and down, so I can always adjust volumes if I want to. A through H, I don't want to do it that way. Number keys as piano keys is fine. So left and right changes the waveform. Spacebar starts a song. I think we're going to just change the way some of this is working here. Spacebar is going to do something else. We'll come back to that. Number keys play or stop based on the press or the release. Easy enough. And I want left and right. Left and right. Change my waveform. Never mind. The number keys can be the tone. Okay, well, we need a different key thing for this. Oh, good heavens. Okay. So, volume. Tone generation is a thing here. So, we set the waveform to whatever. Sounds. It's literally just the piano sounds, though. Here's the thing, though. Oh. So all the tones started with the volume. Okay, let's see here. It's like other systems don't need if it's not global, but it's easy to set it like this. We'll be going to see you now. See you later. Sounds good. Come back anytime. I'm interested to see how your sprite system works out. Okay. Oh. Oh. Oh, set tag music. Okay. This actually gets a little bit more complicated the more I ponder the mysteries. So one thing we want to do is Sandbox scene init sounds test. we want to print out what's the expected volume of our sound. So oh, I have a couple of different ideas here. One is to write a little helper function which prints out all the volume information I care about. Because this is basically the base volume for the sound itself. That is then multiplied by the music factor, and then that is further multiplied by the master volume factor. Which I think comes out of game context. Is that right? Okay. We get our volume, game context, music volume, master volume, music volume, sound effects volume. Okay. So when we play back, this is what's actually being done for volume control. You get the volume of the thing times the master volume times the tagged value. Okay. There's no waveform. Here it is. Where? So I have up and down. Master, let's see here. Volumes. Master, music, and sound effects. So and sound effects. Okay. These are just like initial settings that we care about. Waveform square with a volume of that. Okay. For the sounds test, we do need some information. We need the sounds. There we go. We do not need a song. You know what? Actually, sound. I don't want recorded sounds. What I want is asset or sound warehouse asset like that. Okay, get it. Ooh, that happens. We need to set some of this. We'll static cast to an asset from 0 dot set file to our sound asset. Top file thing modulus 0.3f. So that will be m_sound.volume. And it will be the name of it. So that's sound warehouse get key of our sound asset. There we go. Okay. So file, a name, a volume. Let's just put the volume here on 0.3f. Sign, I believe, is the default. I think that's it there. So if we go up or down, and we should log both of those. So went up or down. We should print out this line and this line. Basically, I want an easy way to switch between all the different things I want to test without too much fuss. Oy. waveform. The sound. Have a thing. Let's charge star shape names. No. Sound name. No. Waveform names. Why do we not have this somewhere useful? Oh, it is public. Okay. That actually is quite a bit easier then. Hold on, I just don't have a static waveform name thing. Nope. I guess I don't. Okay, well, we should probably do that. That's easy enough. There we go. Oh, let's just get the name. Go. We get an integer version of our waveform, and that's it. Now over to Sandbox. You have that. That's good. Okay. Okay. If we change the volume, that happens. Tone generation. If we switch between the waveforms, okay, easy enough. What else have we got here? All right, I need a way to switch between recording playback don't really need that anymore. Well, we can. Why not? We don't care about the efficiency of this code at all. So let's see here. Input, what's it called? Bracket, left bracket, right bracket. Okay. Left bracket, right bracket. What we want is this. These two lines are fine. What we need is int sound index equals sound asset as an integer. Left bracket should subtract. So sound index decrement if sound index is less than 0, then sound index equals sound warehouse entry count. Pretty sure that's just public information. Yes. -1. So in this case, we're going right, so we add if this is greater than or equal to that, we background equals 0. And then set my file. So volume, recordings, tones. Tones play. Where is, I thought I had space bar in here somewhere. Nope. If our sound is playing, sound.play, or stop. If it's playing, stop it. If it's not playing, do that. So left and right bracket, if underscore sound dot is playing, stop it. There we go. All right, let's try this. Oh, and the other thing we want to do, let's just run like this for a second. I made changes to the sounds. So I think that is correct. All right, compile, run, temp.org. Sure, we can save that. Okay. Oh, what this let us do is it let us cycle through every sound pretty quickly and mark whether it's mu-law encoded or not. If it sounds okay, we'll keep the mu-law encoding, because for us the biggest files are the music files, and right now those don't sound off with the Mulan encoding. And everything, if I remember right, should be Mulan encoded. So we're not going to get the full 25% scale in size. Oh, good heavens. Okay. Oh, we didn't close off the thing. I know what's going on. There we go. Oh, class song. Oops. Ugh. Not for me, so it's not song, it's sound. We'll play with songs some other time. That is actually kind of a fun little side tangent I want to do. Some sound. Oh, I probably just named, didn't I? Yes, I did this several places, didn't I? All right. So in theory, we can run this bad boy. Go to Sandbox, which is blank. There's nothing in it, but our tones play. Oop, what? They're not playing. I know what we did wrong. Update sound test. It's not looking for keyboard input correctly. Okay. All right, Sandbox. Let's see here. Still don't hear keys. Why is that? Oh, music volume is scaled wicked low. It might just be too quiet. All right. All right. This is taking long enough. Okay. So there's our chime. Chime. Okay, we have some logic issues. Oh. Once we get the sound index, we then have to set it. Asset equals sound warehouse. Asset sound index, set file, sound asset. That's two very important lines right there. Up, down, left, right. Number key 1. C4 on, C4 off. All right, let's try this out. Okay, so that key is working, but the sound is not playing. There's our chime. Click. Chime doesn't sound bad. Click sounds fine. Error 1 does not sound good. Error 1 should be PCM. That's what I decided. Oops, not that one. Let's see here. Error 2 also sounds terrible. Gosh, wind sounds terrible as well.
You still have a knife? Daddy, you still have a knife?
Whoosh one sounds terrible.
Daddy, you still have a knife?
Go play. I do wonder how much space we're actually going to get saved in this way. Okay, whoosh 2. It's got that bad artifact sound as well. I don't think these are the biggest files. Crumple. Sounds fine. Shut door sounds fine. Except word does not. And reject is going to have the same issue. Yep. And click sounds okay. Keyboard click sounds okay. Page turn sounds fine. Scribble sounds fine. Typing sounds fine. I don't like that thumb. Okay. Whoosh down. Doesn't sound very good. Whoosh up has the same issue. Too bad. Okay, a bounce. Oops. Bounce. Bounce sounds terrible. Pop doesn't sound very good either. Arrow shoot, arrow hit. Don't sound very good. But the arrow miss sounds fine. Scream? I'm not sure. Maybe what I need to do is we'll actually decide Scream 1, Scream 2. Scream U, Scream PCM. We'll try this both ways just to see. Just to see. Okay, rain. Sounds fine. Birds. Sounds okay. Rocket. Seems fine. I'm 99% sure that Cerebral 5 and Rhythm probably are okay. Music tends to sound okay. It's in the right range of frequencies. We're going to listen for a bit. I'm not hearing bad artifacting. Next one. Not hearing any bad artifacting yet. Yeah. I think we're good. I think those are all fine in Mulan encoded, which is the big deal. These ones are the big files. If some of these smaller ones have to be PCM, I'm not too worried about that. So let's go to re-embed our audio using the new determinations. It should tell us that we've got pretty good compression, actually. The files we put back to PCM aren't the most important big files. Those are the music files. So I think that's it. We've got almost 25% compression. Now to test it. Let's go to application. Scene manager, load scene, Sandbox. We'll rebuild our audio. Okay, so just about 25% compression on the audio itself. That's not bad. The files we put back were not big contributors to our space, so This is going to shrink our executable size considerably, assuming all the sounds sound okay. So our sound warehouse is now, what, maybe 1 million lines of binary data? That's not too shabby. Should not take longer than about 15 seconds to build that, which is still too slow for me, but what do you do? If we want any other compression, that's a separate question. I do wish I could get a better lossless audio compression, but I think the work to do it would be monumental. It would be large. What we've got coming up, though, is image data. That will probably be a disproportionate amount of work. Oh, the chalk archer. Okay, fine. Re-embed our audio again with that name. Yuck. Rebuild again. Okay. Still, saving 70 megabytes of audio data. Super good. That's both runtime memory savings and on hard disks memory space savings. So I actually kind of want to run this with my task manager running to see how much RAM we take up. Because all this stuff is initialized statically at the startup of the application. So we'll see our mean memory usage right off the bat. But yeah, our game should be able to run on a toaster. Our memory requirements are tiny. Our CPU requirements are so far pretty small. The biggest issue is the GPU draw calls, and we're not doing that many of those. So I think we could just about run on a potato, which is the goal. Keep it small, keep it simple, keep it tight. We don't abuse the resources of our players, of our users. Okay. Ready to test. I'm not getting the waveform to play. That's awkward. Huh. Anyway, so first up is chime. Sounds good. Click. Uh-oh. Uh-oh. What's going on here? Playing two sounds at once? Jeez, okay. Whoa. We have broken something. We have broken something. Darn it. We're not getting the right number of samples. It's playing past the end of the current sound into the next sound. Yeah, our total RAM memory is 41 megabytes. What a nice small program we've got going on here. Okay. So when we are playing back a none waveform, this is the main issue. Oh, is that true? Is that the main issue? Everything we're playing right now is mono. Was that true? Yeah, everything should be mono. Data sample offset. We get our left, we get our right. Oh, come on. Why have I forgotten this keyboard shortcut? Whatever. Well, let's see if we're slowed down. We're not slowed down, therefore it's this in mono. Get sample. There we go. So it's playing out past the size. So if we go to set file, if our encoding is PCM, then our samples get cut in half. And it shouldn't be playing out past the end of the file. That's my theory. I think that's just a thing we moved around a couple of times yesterday and ended up accidentally deleting it. All right. Chime sounds fine. So that's the mu law. I think the second one's better. I think we have to go PCM on the screen. I think we just have to. That's fine. Okay. Next. Let's see here. Next. Rain. Sounds fine. Birds sound fine. Not really worried about the rocket engine. It sounds like a cheap rocket. That's fine. Cerebral number 5. I don't hear any obvious issues. Okay, I think we are good. It's the last time through the cycle. We're gonna run our compression, because now we only have the one scream in there. And this is our number. So in our notes, before, after, I want to search for where compression ratio was 100. This one. This is during embedding time. Embedding runtime and code. All right, before we do that, embedding data, then we want to get the runtime data. And lastly, the code data. Okay. Okay, runtime. This from when we do this. Start up that. Oh wait, not that. We need to rebuild it. Sandbox. We got rid of the extra stream file. Oh, because we do not have 31 audio files. We only have 30. Oh, good heavens. Oh. Almost time for my nap. Yeah, so basically, as long as these sound files sound okay, the music files, those are the ones that are important, I think. Although it looks like I've broken my tone generator for some reason. We may have to look at that. All right, we're getting close, getting close. $111 down to 27 or so megabytes. Like I said, our runtime memory usage is like 40 megabytes. Not very much. All right, now we run this. There's the audio we care about. So yeah, 111 down to 28 megabytes. Go team. On average, a megabyte per file. That doesn't really mean much. Last thing to check is in the shell. If we cd into source, word count lines of warehouse.cpp, and all we care about is this one. So there we go. So before we were taking 111 megabytes. After we are embedding 110, we trimmed the zeros. We're compressing down to 28 megabytes, which is about 25% of our input, which brings it down to 28 megabytes at runtime. So these two numbers computed the same. Perfect. And space-wise as well, we were going from about 4 million lines of data to 1 million lines of data. So not bad, not bad. Done. We're counting that one done. Anything else? Anything else? I think that's just it. Those two tasks are done. Therefore, into our to-do list, we need to grab this thing. And yeah, this is going to be a fun little piece right here. This is it. Not too shabby. Status. Yeah, I touched all of these assets, so this is going to be a bad check-in. It's going to hurt. Background and doodads. Yeah, I've been playing with that offline. Again, it doesn't make a difference till I export it. All the sounds have been changed. Okay, so yeah, git, status git, add everything. But then we're going to remove that temp.org. Git remove /temp.org. Sounds have trimmed leading trailing zeros. Each sound is mu law unless it sounds bad, then it's about 26% compressed size after compression. Boom, done. Not bad, not bad. Okay, now, next task. I'm going to take a quick, well, let's hear. I'm going to heat up water for mate. And then we'll dive into the lovely world of image compression. So hang in there and I'll be right back. Okay. So we are done with audio compression. We are good. We're happy. We're done. We can do all the different things we want in these ways. And it works pretty good. As long as the big files are in dynamic ranges that MuLaw handles well, we're good. Maybe in the future I'll come back around and make a law also a thing, or some other encodings maybe, I don't know. But these seem to be the pretty standard ones. All right. Anything else? We're good there. So into the journal, first thing we need to do is in embed WAVs, we were outputting some file size, raw data output size, and then the compressed file data size. So that's the thing we need to do over in PNG as well for that measurement of how much space can we save. Yeah, so let's go dig into that a little bit. Okay, taking a look here. Wow, okay, my mouse scroll wheel sucks. So here's our data size. I would like to get the file size. Given the file name. Read file. Fseek size tell, and then close. That's really all we want to do here. File size. We have the uncompressed size. Int compressed size. We did something like this in this one. Process our data. So we have our data, we have our size. We want to pass in the uncompressed size. We don't need that. We might need width and height as well. I'm not as familiar with the QOI format, so we'll go ahead and just pass those in. Contents of width and the contents of height. So data, width, height, size. And then we're just going to stub out this formula, not formula, this thing. Data is char star. I guess it's fine. Okay, so size, width, height, uint 32s. Data char star, const, uint 32t, width, height, size, and pointer to a compressed size. And all we're going to do is start by copying, right? Hey, Dravest, how's it going? It's good, it's good. We have our audio compressed about 26% of its original size, and it sounds okay. Yeah, going mono channel, most of the sounds are MULA encoded, but we did have to keep some at PCM to keep the sound quality okay. But now we're moving on to image compression. Our total RAM usage is 40 megabytes. It's not bad. It's probably a little bit more, but that's about where it is. But before we do the actual compressing, we want to measure who is Yerba. Yerba mate. Yerba mate is a drink from Argentina. Yerba means herb, so herb. This is the mate herb. So this cup here is full of yerba mate, and then you pour hot water over it. Aha, yes. I usually don't drink any mate before streaming, but today I drank my first one before streaming while I was working on the audio. So usually it takes me a little longer before I need to fill up. Okay. I think we're going to just say data equals new character array of the incoming size. And then mem copy into data from char star result. Result gets data and copy. I think it's just bytes. And copy. Destination, source, and size. Yeah. Return result. There we go. Process data. Delete compressed. I think that's it. Then we want to log some things. What we're logging is the same as what's in embedded WAVs. So we have this many bytes in our file, which is our file size. Then we have the size that we read for our data, and then we have the compressed size. I think that's it. Byte raw. So there's the file, there's the raw data, there's the compressed. Okay, here we go. Super close. Go find the last embed. This time we're going to do PNGs. There's a lot of extra sprite and tile crap that I don't need to print out anymore. Okay, and then lastly, we do that. I don't think that needs to be a warning anymore. I think we need those. Who is logging? Just UV sprite. This guy is. Don't need that. Sprite. Modulus S. This one. We've looked at all of these. And then all the tiles. Maybe we keep the sprites listed. Sprite available tiles. Frame range. Those are nice for debug, but needed. PNGs. Okay. Run it again. That should not be a warning. These default offset values. That's an error. Yeah, a couple of these warnings don't really matter. Okay, clean this up. Put files, there's our sprites. There we go. So if we read in a 800 kilobyte file, that turns into 8 megabytes of raw data. Oh, 0 bytes compressed. That's not very good. Okay. Bedwabs. We kept those 4. We basically want this. File, that. Okay. Put this near the top. Total image size. So that's easy. Total file size. Actually, let's do this outside of here. Let's do that right here. File count increased. File size plus equals our file size. Total image size plus equals the contents of the size. And our compressed size plus equals our compressed size. Easy peasy. Okay. There we go. So 100% compression means we haven't done anything to it. Oof. The files themselves, because they're PNG, and PNG has some pretty aggressive compression algorithms. The file data is much, much smaller than our actual image data that we're embedding. But this number probably matches what's up above. We're doing this. 633112. 633112, yeah. Okay. Why is it writing this statistical information before the image? Output file contents. Writing file. Oh, I see. Because the way we write these out. We're going to log that. If not, if the function fails, error. All right, let's just see if that makes our output look the way we want. That's better. Name of file. So if we can get anywhere close to that compression, we'll be happy. Like I would be fine with even like 16 megabytes. We got that down to 16 megabytes here, the compressed data. For like a, what's that, almost a 25% compression ratio? Okay, so we did that task, journal. I'm not sure this is gonna really format the way I want. Okay. Oh, in fact, let's just put that all back the way it was. Okay, so embedded PNGs now has a placeholder for compression and logs out various size information per file and cumulative. Embed PNGs now scrubbed out and ready for size optimization. Okay, now to the actual task. We're ready, finally. We're 2 hours in. That's not too far off where I want to be. What we want to do, let's see here. There's a what was the YouTube channel? I had this bookmark on another account somewhere. Um, 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 um. I think this is the one. Here you go. Educational video. How PNG optimization actually works. Now, at the end of it all, so at 23 minutes in, he talks about the quite okay image format. And that's what we're, so for 23 minutes he talks about PNG. We're not using PNG. I mean, our raw images are PNG, but what we embed is just image data. But we want to compress that using the QOI format, which may be bookmarked already here. Let me just make sure that still works. And it's an image format whose entire format fits on a one-page specification. So without me actually knowing anything about how this works, we're going to try to do this. The QOI file consists of a 14-byte header, which we will not store, followed by any number of data chunks and an 8-byte end marker. The color space and channel fields are purely informative. Okay, so we're gonna look through this. We're gonna read through this. Let me see. Maybe I should share what we're looking at here. Does this work today? No, we have to play silly games. Okay, and it's for some reason sharing my browser sometimes ends up with some bizarre behavior. So here's the quite okay format image, the QOI. And we're going to try using it. One-page specification. We have a 14-byte header. These are informational. Row by row. So we do need the row and height information. Left to right, top to bottom. Which is, I believe, how our raw data is laid out anyways. So we can just walk through our array. The decoder and encoder starts with RGB 0 alpha 255 as the previous pixel value. An image is complete when all pixels specified by width and height have been covered. Pixels are encoded as a run of the previous pixel and index into an array of previously seen pixels. So we're actually going to save a ton of information here because we have so much alpha data, even in our very packed up stuff. We're going to save a lot. An index into an array of previously seen pixels, a difference to the previous pixel value in RGB, or we get the full RGB values. 4 different ways. So each pixel has one of those 4 options. A colored channel is assumed to not be pre-multiplied with the alpha channel. I agreed. A running array, 0 initialized, of previously seen pixel values is maintained by the encoder. Each pixel that is seen by the encoder and decoder is put in this array at the position formed by a hash function of the color value. In the encoder, if the pixel value at the index matches the current pixel, this index position is written to the stream as index. This is the hash function. Each chunk starts with a 2 or 8-bit tag, followed by a number of data bits. The bit length of chunks is divisible by 8. All chunks are byte aligned. All values included in these data bits have the most significant bit on the left. Eight-bit tags have precedence over 2-bit tags. 7 zeros and a 1. And then each chunk. Okay, that's kind of clever. Interesting. This doesn't look that bad. RGB, RGBA, index into an array. Difference between this byte and the previous byte, colored. But only if there are small differences, which makes sense. A lot of images have a very small difference between pixels. Storing the actual RGBA value is really bad. Instead of 4 bytes, you're storing 5 bytes. Okay. The difference between the current, so 1 to 2 will result in 255, while 255 plus 1 will result in 0. Okay, so there's a wrap function in this diff. Unsigned integers with bias of 2. So this is if no alpha difference. OP Luma. I know there's a reference implementation of this encoding, decoding as well, but I think we can write our own. This doesn't look that bad. This is not crazy weird math stuff. This should be things we can figure out. So there is a reference encoder decoder. I think we can do it. We're looking at the specification, benchmark results. Oh, he has test images. Good. Lossless image compression in big O of n time. Yeah. Wait, he has an OK audio format? Oh, I haven't seen this. I haven't looked at it. We might have to switch over to this eventually. Hmm. "2023, that's why I haven't seen this. I heard about this a while ago, but or the QOI. Okay. This one also lossless? Um, 3.2 bits per sample. That's better than time domain audio compression. Yeah, I understand all that. Lossless, good, meh. So it is somewhat lossy, but I mean, encoding is lossy, and that's 8 bits per sample. This guy's claiming let's see, where's the paper? There's not that one, this one. A format that is lossy, simple, and quite okay. 3.2 bits per sample. QOA. It is lossy. A constant bitrate of kilobits for stereo 44100. Huh. And he has audio samples. Oh my gosh. Oh. We might have to support this. Building a game, play some sound effects and music, your options are quite dire. Yeah. Okay. Yeah, we're kind of dealing with the big file sizes thing right now. Oh, man. I didn't know this existed. Otherwise, we would have completely skipped the MuLA encodings. Okay. Oh, man. That makes me sad that I've missed this. Voodoo. Oh. Tech. QOA for audio, question mark? QOA, what am I doing? Okay. All right, so we're gonna stop sharing this thing because you've seen, let's see here now, let's see here. This is the document we're gonna be looking at. I've put the link in the chat, so if you want to follow, this is what I'm looking at. We don't have to support everything either. So anyways, this is the reference I'm going to be talking about. I have to figure out where my mouse is since there we go. I should get my mouse back now. OBS loses my mouse if I share the browser and switch between windows and do things that OBS doesn't like. Okay, so that's the reference implementation of QOI. So what we're going to do is we're going to make a new thing called test QOI dot cpp. No, it's going to be our main file pound include. Oh, let's see here. How did Encoding do it? We're going to need this. We're going to need. Let's get our logging. Up over to source log. Int main int argc char star arg vector turn 0. Okay. So we have 3 steps we want to do. 3. Read PNG char star file name I need a width and a height. Let's see here. Raw image. Let's just put all this in one place. Data, int width, int height. Initialize a raw image read file name into a raw image. I'm going to start from here. All right, initialize image point to data equals null pointer, image width equals 0, image height equals 0. Size return 4 bytes times image width times image height. Constant expression, megabyte, 1024. Actually, we'll just do this as a double. Times 1024. Okay. And then we'll have read return the file size. Everything else good? Okay, so step one, we need to initialize our image. Init address of image. Size of our image. So log note. Image size should be 0. Read into our image or v1 or something. We'll think about it. Whatever. So int result. Over here is basically where we do this. First, we get the file size. File name, blah, blah, blah. Result equals that. Close, return result. Image size. All right, read. Reading file name. Then this thing. Okay. So we load into the address of image point to data, image point to width, image point to height, and then the file name. I think we need the address of these things. If there's an error, it fails. Otherwise, we're good. Init read. Clean up. Raw image, star image. That's the thing we need to do. Clear. What do we call it? Clear. Sure. Image point to data. It's not equal to null. Delete image data. image data equals null. Image width equals 0, image height equals 0, there's clear. Init and clear are very, very similar. It's fine. Okay, so we init, blah, blah, blah. Clear. And that should give us back the original image size of 0. Anything else we need to do for starters? All right, makefile for this guy. It's a little bit different. Make build target equals target.cpp outputs that, so that's fine. We can do this. Compile build target equals test QOI. Okay. Int to unsigned int. Okay, can do that. File size, okay. Okay. We have from the QOI website test images, which we're going to put, I guess, on the desktop. Fine. Going to extract it. Okay, now we have PNGs and so let's see here. Let's take a quick gander. For edge cases, this is a small file. QOI logo is pretty small. Test card. Okay, that's pretty brutal. Test card RGBA. That's probably the one we want to start with. 18 kilobytes. Test card RGBA. So we want. Maybe we just do this hard coded for now. That's not what I wanted. Load it in. Do I have size information for that width and height? Maybe if I open it with GIMP, I can get that information out here. So it says it's 18 kilobytes. We will eventually run through every test file in here, but we don't need to worry about that just yet. So there's our test file, and it's 256 by 256. Okay. read. We're going to copy that file name. So init. Oh, let's just call it label. Label. Clear. Read. Erlen label. Label. How was the Christmas dinner yesterday? It was delicious. It was good. We had like a pork roast and potatoes and gravy, mashed potatoes and roast vegetables, and then a chocolate cake and ice cream. It was great. Had a nice chat with my parents. I had to run out early though. I had a city council meeting last night, so that's always the sad part of a Christmas dinner. It was very nice. My kids mostly behaved themselves, I guess, until I left. So, I mean, what more can you do, right? Okay. All right, sounds pretty good. Yep. Not too shabby. Not too shabby. Um, just the modulus d image point to width, image point to height. Image point to label. I guess that's kind of it then. Okay, so ampersand image to image. There we go. Yeah, it's nice. I like Christmas. It's comfy, it's cozy, it's all good. So the other thing we might want to do. Okay, so in theory, we're creating an image, we're getting a handle to it, we're initializing the image, logging the image, reading a file, seeing how big the file was, then logging the image, clearing the image, logging the image. Okay, so we're going to do a lot of image manipulation. We might as well just have this tested out right off the bat. Too few functions, yeah. So test card RGBA. I'm not writing a whole thing to process the PNG file name into something shorter. We'll just pass it in instead. All right, then /tools bin test QOI exe, and it blows up. Run. It exited normally. Oh, right. We should do that. Now it's crashing. So our image is 0 by 0, therefore 0 bytes, and we don't have a label. Then we read the file, and the file size itself is about 18K. That's great. Then we get a seg fault somewhere. Image. Where the arguments are an empty string. If we read, get our length, image label, copy in, stir copy. Is this one of those destination then source? Oops. QOI. Wrong order. Piece of cake. There we go. There we go. We go from 0, we read the thing, we have the file size, which expands out to 262 kilobytes from 18 kilobytes. 256 bytes. Okay, so we're reading in the PNG just fine. We have some standard operations on integers, on images. So test QOI. Coming along slow but steady. Now, I don't want to write out a PNG. I only want to read it in. Then I want to write out a QOI. But there's two parts to the QOI. One is the header and one is the payload. And I do not want to write a header anywhere. I just want the payload, but test, I need to be able to see a QOI. I'm not sure I have a program that'll open a QOI. Hey, Natsu, how's it going? Thanks for the follow. We're working on some image compression. We're going to use a QOI format, and the QOI specification is in the chat. Let's see. We should probably pin that actually. I'll unpin at the end of stream. So there you go. We're looking at the QOI format. Small, simple, not as good at compression, but it's not. It also is much easier to shrink, much easier to encode and decode. It's a one-page format specification, so we are happy with that. All right, so we're pardon me, we're reading in a PNG using the load PNG. It's a single file include, no library, no linking, which is the way I like it. It leads in our image data. Now we're going to try to interpret it to QOI. This is where things get interesting. QOI I think maybe we just namespace this sucker. We have encode. We have a decode. Let's see. We want star data int data. Let's see here. Int width, int height. So this has to be raw data. Raw. These are raw image data. So every pixel is 4 bytes. Red, green, blue, and alpha. Then width and height. So 4 times width times height is the size of our raw image data. Then we need to output the size. So char star encode and int size. Decode is going to be very similar. Char star decode, char star QOI, int width, int height, int size. This does not need to be a pointer though. QOI.cpp. So that's encode, decode. There is all of the header information. So yeah, I'm not going to be flipping back and forth between my code and the reference sheet. So you have to go to the reference sheet, see what kinds of things I'm talking about. Okay. 1, the magic number, the width, the height, the channels. We are only going to support RGBA in the color space. You kind of want to know. I can open this with GIMP. Where's my GIMP? Okay, well, current GIMP doesn't. Okay. We could look at this file in Emacs. There's QOIF. Let's look at this in text mode. So there's our QOIF. In the specification, we then have a width and a height. So that should be 256. That's 256, right? So if we go 0248 1632, no, 1248 1632 64. So anyways, width, height, channels, 4. That's a single byte, and then color space, he has it at 0. And that's it. That's his header. Okay, so we understand the header. That's a piece of cake. From there to there. I'm just talking about image payload. So maybe we start with the following. Right. Const char star file name char star QOI int width int height. We also need the size. Right. Int size. Read. Let me think. Read is different. Const char star read. So we go from file name to this buffer. We know it has a width and a height, and this is the size that we read out of this file. We write to this file this QOI data. Actually, whoa. Okay. Read write to the file name this QOI with widths, height, and size. Is that how I want to run this stuff? If I read a PNG, call encode, then I should be able to write the payload with the header to the file. Is that good enough? Get our size, we output our data. If result is not equal, oh, let's see here, if count is not equal to size, that's an error. QOI dot read modulus d bytes read modulus d bytes expected, which is count and size. Out data. There we go. Length of width equals 0. Height. Size equals 0. Okay, so we read into result. Then we close if it's not the right size. Error. Done. I don't really need that one there, but this one. I mean, either, whatever. We'll do it the old-fashioned way. Otherwise, we have a buffer with all the image data in it. We're looking for the correct file format. So when you read a file format, there's often a magic number at the start. That's the first one we're going to look for. So we're going to take our result buffer, and we're going to do a uint32t magic equals read this out like that, and then get the contents of that. Magic numbers. So we need to make sure it's a QOI format. We can do this a couple ways. You could do a stir and compare. We could read off the 4 bytes and compare it to a number. For example, it's true. Okay, so we've got enough there. Make file. Let's see, it's somewhere near image warehouse, maybe, or texture. I don't really know where it goes. QOI.o. We'll put it after math, I guess. Objects. QOI.o. There we go. Includes C standard input output and C string, please. C standard int. No return statement. Yeah, agreed. What? Why is this building the image warehouse? I don't need the image warehouse. Okay, that looks about right. So this is going to be test png to QOI is a thing we'll have to do, and test QOI to PNG. Okay, there we go. Parts of it are coming together. I do have a bitmap writer. It's not my favorite. Let's see. Where are we at? 3 o'clock. Okay, so that shouldn't have changed anything. Should all still print out the same stuff. Yes. Okay. QOI to bitmap. Maybe it's actually MP. I have bitmap writing stuff somewhere. Heyo. Adam Fighter, thank you for the follow. Let's see, what's that? 1, 5, 5 plus 8 or so. Adam Fighter, 10101. Oh, depends whether it's hexadecimal or binary. But 1, 2, 4, 8, 16, 21. Adam Fighter 21. How's it going? Welcome to the chat. Welcome to the channel. 21, yeah. Had to think about that way longer than I should have. Ooh. Well, welcome aboard. I was definitely looking at that as binary, but 10 plus 10 plus 1 works as well. Nice. Cute. Well, we're building a game with no game engine, and we're trying to compress our image data. And instead of using a real image compression from like MP3, like a JPEG or PNG, we're going to use QOI. I've pinned the format specification. That was a joke. It is binary. Yes, but it's a clever joke in that they're both true statements. You get the same answer both ways. Yes, very good. Very good. Oh. Yeah. It's my router address. That's the lock on my luggage combination, right? I use MingW in Windows. Hey, me too. Me too. Yeah, I've used Mac. I've used Linux. Lots of different Linuxes. Linuxi. And it just at this point, if I'm in Windows, I'm going to install MingW. It's just less painful than trying to remember how the old Windows shell works. It's too bad people don't provide more library support for it. You know, I actually haven't had that much trouble with it, except the Steam libraries. Linking the Steam libraries, I can get it to launch from Steam, but I can't get any support for things like getting a username, getting their account, like not their account ID, but basically their account ID. I can't get their I can't get anything to work. Achievements or leaderboards. I can't do any of that from MingW. So you can launch it in Steam, but that's it. So our game is going to be a little bit simple when we launch, which I guess is fine. Yeah, Steam, I mean, that's been a thing for years. I went back on the forums, and Steam has never, ever supported MingW. I think people tried to make a shim thing between it, but I'm like, that's too much work for me. I don't care that much. Well, you're obviously a computer user if you're using MinGW. Programmer, software developer. Program in C, C++, Python, MATLAB, Java, Awk, Bash. Yep. Okay, so you've been around. You've done some things. That's good. PostScript. Cool. What kinds of programming do you do? Embedded? I mean, if you're a Linux kind of person, either web development. You said Java. Yeah, so maybe some web development in there. C, C++ though, so you're doing some systems programming. It's not bad actually. Okay. Well, I have beef with almost every language I've touched, so like I won't program in Java voluntarily anymore. C, C++ I'm fine with. Python I'm fine with. I have used MATLAB and its open source version. What is that? Octave, I think. I do. I don't know. I've done some Bash scripting, but I'd rather write things in Python. I think ultimately it ends up being easier to maintain. Which isn't to say that I can't do the bash scripting, but I always have to look stuff up because I don't remember from when I need it to the next time. I enjoy C and Python. Perfect. I agree. There are some aspects of C++ I like, but yeah, C is pretty close to being just about right. CPP can get under my skin. Yep. It has C++ has grown too big syntactically. Like if C just had like function overloading and operator overloading, that's almost all of the complaints I have about it. Not quite all of them. It would be nice if there was a better meta language than just text replacement with the pound defines. A little bit of modularity, so it's not the pound includes aren't too weird. But yeah, C's pretty good. I wrap a bit of C up with some C++, and I'm happy. Yep. Okay. In theory, we should be able to get this log statement out of that printout. So let's try it. Unused variable. That's fine. We shall delete QOI. Hey, we have two different magic numbers, and they're not the same. 690. It's the whole transposed bytes. Okay. I swapped the 16-bit words. I did not swap the bytes correctly. Okay. Don't know why exactly I did that, because these two have to swap, which I knew when I did it, but oh, come on. Oh, he snuck in a 666 and a 69 in there. Look at that. What a clever guy picking out his magic numbers. So it brings you here. We're towards the end of our game development. We're trying to compress our size. We have no dependencies. Everything is completely statically linked in. Well, 4 dependencies, statically linked in. All of our image and audio data is completely embedded within our executable. And we're just trying to shrink that now. We were at 111 megabytes of audio data at the start of the week. And now we are at, well, here you can see the whole numbers, I guess. We were at 111 megabytes at the start of the week, but today we've got it down to just about 28 megabytes total, and that's both when we embed it. We also recompute it at runtime when we start up and initialize all of our audio data. So we're getting that. Then we're going to also try to compress. You can see our image data is about 64 megabytes. We're going to try and compress that using QOI image format. I saw C in game dev and low level, no dependencies. Yep, okay, all right, well, that's what we're here for. That's what we're here for. So, I guess we could show the game itself, just so you know what we're working on. Source, builds, debug, word sleuth. Like I said, the game is... Oh, that's right. The game is basically done. You can type in words. That tells you how many letters match the actual thing, and then you make deductions about what the word is. So prime lunch toads, ultra, demon, laced rhino, cloud, lines. and then we try to guess what the word is. A, D, oh, T, R, A are all in, so that's easy. I and O have to be out, which means D and S have to be in, no EM, and no P. So, darts. Hey, we did it. Different game modes. We also have some little interactable doodads for people to fiddle with on the chalkboard. Things like, you know, a bouncy ball, bubbles, that kind of stuff. Pop the bubbles, watch them bounce. All very mesmerizing. So yeah, just having fun. I like the classroom-like environment. Thank you. This is a blatant ripoff of a 1992 game called Wordbreaker that I played on the Macintosh when I was 19, when I was very young. I've added some improvements to it, but the main idea, the main flow of the game is all there. So the game's done. I'm just compressing the size. Then I got to make a web page and a trailer video. Get that all uploaded to Steam, so it shouldn't be too long. Early next year, maybe. I am not a video editor or web developer, so it'll be a static website. The trailer video is going to be very simple, but yeah, that's what we're cranking out today. I have a Discord, which is pretty quiet. I basically just announce, oh wow, that did not work. Paste. That did not work. Interesting. Okay, invite people. Copy the link. Copy. Okay, I think that's it. No. What? All right, I have shared out this Discord channel server thing before. Invite people. Huh. I think they have... No, not that one. Not that one. Let's see here. Yeah, for some reason Discord isn't sharing it. Anyways, sheesh. Well, on Discord, I am the discourager of hesitancy. There is this Discord server where you can get announcements or chit chat about just about anything. Yeah, Discord itself won't let me copy the server link. Delightful. Anyway, technology. This is why I don't update my software. It was all working fine. Now I can't get the server link. Invite people. Like, this is actually bothering me. Wow. All right. Well, screw that. Yeah, you can hit me up on Discord, the discourager of hesitancy. Anyways, yeah. So, trailer, website, binary compression of our data. Yeah, today is QOI compression. We got the sound all optimized. So what we do right now, let's go back through that, I guess. Embed PNGs. What we do is we have our PNGs. We read them in using, and this is not in-game. This is outside of game. This is our asset pipeline. We load it in using load PNG, which if I'm going to read PNGs, this is one. There's no library. It's just a header-only file. We read it in, and that gives us our raw binary data. Then we write it all out as actual binary data. So this thing right here, which I'm not going to show the image file because that's a million lines long, but we do the same thing with fonts. Our fonts are all stored in a binary format as well. So this is what a font file looks like in C, right? And we can look them up by index, or by, we can look up the name by index and all that. So this is what we're doing to image data. We get we read in the PNG, we get the raw image data. So it's 4 bytes per pixel for red, green, blue, and alpha channel. Now we're trying to compress it. So we get that 60 some megabytes down to something more reasonable, just to shrink our executable and our memory usage. My server is called the Discourager of Hesitancy. Yes. Yes, it is. Invite people. Copy. That's just copying. It's copying the hidden use copy button with the copy button. That's just delightful. So yeah. Anyways, we do that Monday through Thursday. We crank away on the game Monday through Thursday. And then Friday is compiler day. We're taking a long, meandering detour through tokenizer generator. But yeah, that's Friday. That's the keep ourselves from getting too mono focused. Give us a break. So yeah, welcome aboard. Let me know if you have any questions. Otherwise, I just kind of code and talk stream of consciousness. Somebody hits up the chat, and then I jump in with whatever they ask about. Happy to go into any level of details or look at any other code. Like if you're like, oh hey, what does write bin do? No, we can go look at it. It's whatever you want. Otherwise, I'm just gonna work away. I'm sometimes I don't see the messages right away, but I try to keep on top of them. It's not like my chat is so busy I can't get work done. So I don't mind the occasional questions and whatnot. You can try dithering to compress more. Yes, yes. I've been fascinated by this QOI format ever since I saw this video. Where is it? This one. I'll put it back in the chat. The video is the first, I don't know, 23 minutes or so. Is about how PNG compression works. And that's actually kind of interesting. Quite informative. But QOI, he like jumps into it, and he starts talking about it at about the 23-minute mark on that video. So the QOI format is the pinned comment at the top. It's a one-page format specification for image compression for image file format. It stands for quite okay image format. I hear PNG is one of the hardest formats. Yeah, once I saw that video, it's the reason why is because it tries different compression formats, different compressions, until it finds one that works well for the image. But yeah, QOI, it doesn't get quite as good a compression all the time. It's comparable to PNG, but its decoding is so fast and it's simple. Like this QOI format is one page. So we're going to try and do that today and tomorrow. We'll see if we can get QOI format in one day. I pinned the format specification up top. So if I reference the format, I have it open, but I'm not going to be switching back and forth between my code and the format over and over again. So we're just in the read the file stage, looking at the header. But yeah, that's what we're doing today. We'll see if we can get that 60 megabytes of image data down to 30 or 15 megabytes. We aren't going to beat PNG today, but if we're close, it might be good enough. And I don't have to support anybody else's crap. We're not exporting images. This is literally just to put the image into my executable, and then my executable will display it. So I can put it in whatever format I want, whether it's widely supported or not. Okay, now our numbers look the same. Yeah, when I word swap, I should have also byte swapped. Okay, so this thing, let's see here, you meant 32, actually, let's just pound define it. Magic number, 0x, whatever. If magic equals Magic number. We're happy. Otherwise, it's a reason to bail out. QOI format looks concise and intuitive. Yeah, I mean, just reading through the format, it makes sense. Like it's, you only need that one page. He's whoever came this up with this, whatever his name is, Dominic. Yeah, that's readable. He does have an example implementation, which I could just go rip off, but I'm not going to. I'd rather build it myself and just see how it looks, see how it works. I did steal his example files, so those are the ones we are using, but yeah, I'm liking it so far. Like I said, it's not going to compress as well as PNG, but it's going to be pretty good. So looking back at the format, we find the right tab. So we look at the magic. We can get the width and the height out next. Actually, width equals, let's see here, offset equals 0. Offset plus equals 4 bytes. Okay, contents of width equals that. Oh, I guess we need one more print around that to make those match up. There we go. So we get the width, we get the height. We could write a macro to make this all much more convenient, but whatever. Width, height. In fact, we've done it elsewhere. But then we get uint 8 channels. And color space. Channels, uint 8 result plus offset plus a byte, and then color space. I'm kind of at the point of wanting to get that scan function out of somewhere else. We have this in replay, if I remember right. And define scan. Basically only useful here. Memory copy into a destination, the size of the destination. Yeah, so we should be able to do magic. Then we scan into magic. Result plus offset. Offset plus that. There we go. Scan into the content of width. Height. Channels. And color space. There we go. That's a little bit more readable. If magic thing. You could literally just log out some of this for now. Log. All right, good luck with the project. Thank you. Yep, you have fun eating, but yeah, drop back in anytime. Always welcome. Modulo Steve by Modulo Steve. With height. Channels. Color space. I really don't care about the color space. That's what we get. What's going on? All right, so now we compile that. Okay, it's not right that we have 4 channels in a color space. Oh. $65, $536. Unit 32, width and height. Okay, let's do this then. Width, height. We aren't getting weird behaviors. That's not right. Oh, it is. Hmm. We get our magic number, width, our height. It's getting channels of color space correctly, so what's wrong with this thing? Is it a byte ordering issue? If we completely byte swap this, we would have 0, 1 here. That would be 256. Yeah. Okay. Hmm. magic number, then width and height. Channels and color space came in correctly. The magic number came in the way I would expect. Width and height. I need a Indian swap value, which would be, oh, Indian swap 32 bits. We have to swap 4 bytes. This one is value downshifted 24 bits. This one will be value downshifted 16 bits, 8 bits. Ending this swap. Oh no. I remember this. It shifted 24. So we take the high byte, moved it over 24. Then we move this one 8, 16, just 8, right? And this one goes 8 bytes that way. So that's off the 2 middle bytes. Or it will. And that gets bit shifted 24 bits. W equals Indian swap W. Same for H. $256 by $256. There we go. We have to do some Indian swapping. Okay. And that gets us through the header. We're through the header. We're done. Cool, cool. So when we read, okay. We're gonna have to delete result and set width, height, and size to 0. Invalid file format. Okay, if we get the magic number, we now have the offset, this offset here, to our payload, this offset. So we should then be able to scan our payload right here. So in test QOI, QOI bitmap. QOI loaded modulus D by modulus D, and it was modulus D bytes in size. So width, height, size. I may have too many. Oh, that's a little strange. Size equals 0. Size, oh. Wow. Contents of size, contents of size, contents of size, contents of size. There we go. Ah, wrong file. Hey, there we go. QOI loaded 0 by 0. Oh dear. Well, that's unfortunate. Oh, I know why. I didn't actually do the right thing here. Width equals W. Height equals H. There we go, 256 by 256 and our file size. Cool. All right, I'm going to pause briefly for a restroom break. Then we'll start scanning through the image. So here we go. Be back in just a minute. Okay. Now, we have loaded the QOI. In theory, we need to turn it back into raw data. Right bitmap. There we are. That's it. That's a bitmap there. So maybe we steal this code. That's not too bad. Okay, but that's not the important part. QOI. That's an encode and a decode. So if I read it in, there's my QOI, I have my width, my height, and my size. Do this d bytes. And a label. Okay. All right, so we've loaded the QOI image. And I guess what we want to keep is the office. Oh, let's see here. Read it in, and we decode it. Decode should be const and should encode. Okay. QOI gets the width, the height, and the size. So when we write out a bitmap, that's all we need. Just throw out the width and the height. Okay, so we're going to consume the header, which is 14 bytes. I like that it's a fixed size header. I think people get a little bit too overexcited about. And then an 8-byte end marker. 7 zeros and a 1, if I remember right. This OP Luma, as opposed to OP Diff, I'm not sure I understand. 2-bit tag, 1 0, 6-bit green channel difference from the previous pixel, red channel difference minus green channel difference, blue channel difference minus green channel difference. I'm not, this part, green is used to indicate the general direction of change and is encoded in 6 bits. The red and blue channels base their diffs off of the green channel difference. Values are stored as unsigned with bias of 32, bias of 8. Alpha channel remains unchanged from the previous pixel. Run length 63 and 64 are illegal. That makes sense. Okay. OP Luma is, to me, the most confusing. Decoding it is not hard. I know what to do with an op diff and an index and a run. And when to use these. That all makes sense. This one I don't understand. It's not, I don't have a vision of when I would look at a pixel and be like, oh, clearly I choose the Luma option. 2 bytes. Like I said, I know how to read it out. I don't know when to choose to use this. Run is obvious. Diff is an easy check. Op index is an easy check. Zero initialized. Yeah, I understand all that. I understand everything except this one. So if it's not a run, a diff, or an op index, then we try a Luma and we see if we can pack enough data into 16 bits that we don't need to resort to this thing. Because I think this means, what I'm guessing at based on what I know about color theory and RGB space, is green largely determines how bright your color is. And so this is for when your hue isn't changing, but your brightness is, which happens a lot, like shadows, right? They're actually very, very close to just the same hue, just down in brightness. So if you change the green by a large amount, but not your reds and greens, reds and blues, then this might be a very efficient way to store it. Is that what it is? Green is used to indicate the direction of change. Red and blue base their diffs off the green channel difference. Okay. Well, we start off with the color. Easy enough. RGB alpha. Code. Let's go to QOI. Const int header size is 14. There we go. Nothing else should change here. I could look at the last n bytes as well. Where's my spec? Where's my spec? So run like this stored with the bias 1 of the... I saw it. The byte stream's end is marked with 7 zeros followed by a 1. Good to know. So header size followed by 8 bytes. So footer size equals 8. Okay. Where we're checking weird things, we can set our offset to our size minus 8 minus 9. We need a uint 8t byte footer byte scan footer byte. We should assert certain things here. Assert that our count is greater than or equal to QOI footer size plus QOI header size. That should fix a lot of our issues. If footer byte is not equal to 0, then we error out. Let's see here. I think we do this a little differently. We're going to go to invalid file. If magic is not equal to magic number, go to invalid file. Go to invalid file. 2, 3, 4, 5, 6, 7, 9, 0, 0, 0, 0. 7 0 bytes and a 1 byte. 1, 2, 3, 4, 5, 6, 7, and a 1. So basically jump to the footer. Okay, as long as all of that happens, that all happens, this if is no longer a thing. Nope. Let's see. That's the end of the file. Assert was not a thing. Okay, QOI. C assert. Alright, we're getting there slowly but surely. Slowly but surely. Decode. Unused variable raw. Decode. Char star int. Decode char star int. Oh yeah. There we go. Oh, wrong one. Okay, nothing should be broken. Error, invalid file format. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, and an 8. I'm trying to decide if I like this footer or not. Hmm. Hmm. Here's what we're gonna do. The other thing I want is to know what that was. Footer byte. I want to know which byte it fills it on. Hmm. I have some inverted logic somewhere. Very strange. This shouldn't be the hard part. Hmm. Oh, I remember now. Oh, but that was it. Okay. There we go. It loaded and it's happy. It's good. It's fine. Great. Then in we decode. Okay. We need a color. We need an offset. There's several things we can do here as secondary verifications of correctness. One is row and column. Well, offset is, well, it's here. 4. Offset equals 0. Offset less than size plus offset. That's the obvious thing to do, right? We're going to get a byte out of QOI. QOI plus offset. We're going to read a byte. We get this byte. If b equals, this is straight out of the thing here, 1111 is equal to f, it's equal to e, else if b and, let's see here, the two top ones, zero, zero, sorry, just thinking out loud here, or not out loud, thinking there's like so many pieces of this that we have to get going, so a little bit scattered here, but that's okay. 1, 2, 3, 4, 6, C0, there we go. Okay, so we have 0, if it's F, if it's B, so it's 0, that is QOI op index. If it's a 0, 1, get a 1, 4, 0, 1, 0 should be 8. So QOI op diff. Luma is 1, 0. And then op current, next, or previous. There we go. Okay, decode. We need a result. Let's do this. Let's get equals 4 times, let's see, new char 4 times width times height. Assert width greater than 0. Height is greater than 0. Size is greater than 0. Sure. That seems reasonable. Count. Pixel index. So as we march through this thing, I would like to keep track of where I am in the image. And at the end, we can assert that all the things are correct. Let's see here. Back to the old documentation we need. Okay. We also need the hash of recent colors. I'm not actually sure what order this stuff is in. We'll just take a wild guess here. So we're going to take C, and bit shift it 24. We call that good. Green. And 0x F1 blue alpha. Bit shifted 16. Blue is 8. Alpha. There we go. We can sample those if we want to. Okay. I want that scan back, don't we? Let's do this. Let's move these pound defines up top. We could type def, but you know, whatever. We shall undefine all of these underneath here. There we go. Okay, now if we get RGBA, that's pretty easy. Previous equals current. Current equals, what's here? Scan into current. Oh, it can't be called destination, can it? Let me think about that. Offset is fine, but result is not going to work. Maybe we change scan to have a destination from a buffer. Let me assume a buffer plus an offset. Actually, let's flip those. Scan QOI current. Once we have the current value, we go into our I just want to write a pixel here. offset less than size. Let scan do all the work here. Dump into a buffer some value. Then copy into our buffer all right, this is special use enough it doesn't where are we at 437. And a byte. We need 3 of them. 1, 2, 3. Red, green, blue. Index. Hey, Suki, how's it going? How are you doing? I realized today how the tensions between the French speakers and the English speakers in Canada are still very strong to this day, even after more than 100 years of tensions. Yeah, well, and you're in Quebec, so I mean that's kind of to be expected, I guess. Not saying it's good or right, but it kind of is what it is. Let's see. What if we do this? What if we try to do all the work in one line here? Current equals. Nah, it's just our current color equals. Red bit shifted 24 bits, ORed with green bit shifted 16 bits, ORed with blue bit shifted 8 bits, ORed with our current color like that. Just because one person said that a separatist federal party had 32 seats. Interesting. I have not been following that line at all. To write to output. What do we call it? Result. So in theory, that's that. Index. Index. We also have to put this into the array. each color. Yeah, to be right to result. Right to array. So if we have an index, and we look up the color in that index, we really only need the 6 bits. So no, I don't know. The Canadians I've talked to all lived very close to the US border and weren't super French intense about it. So I don't know what's going on there. Okay. Just do previous equals current here. Write that to the array here. Maybe not. Maybe we do that in these actual places. Right to array, right to the result. If we get an index, we don't have to write to the array because we're getting it from the array. We do a diff. You have to do both. Same with Luma. A run should already be in the array, so all we have to do is write to the result. So we're doing a QOI decoder encoder today, tomorrow. We'll see how far we get. For image storage. Right to arrays. So we need our hash. Let's do hash color. Look at this. It's that. Basically, it is red of our color, green of our color, blue of the color, and alpha of our color. Okay. Right to array. Don't have that array yet, but we're going to. It's 64 elements in the array. Color array. 64 elements. have the array. We can now say array at hash of current equals current. Okay. Now, int index equals byte and 0x not C. Let me see. Do I have a calculator up? 1, 2, 3, 4, 5, 6. 3F. That sounds about right. 3F. Equals array at index. Write that to the result. OP diff. Diff is a little bit more complicated. And the luma is more complicated, yeah. Diff, luma, we don't want to deal with those just yet. But the run is not too bad. We get a run. Which is this. Current byte masked with that. +1. Assert run less than or equal to 62. Then we just, I don't think we have to do that. I think we just use current as is. So we read a byte, we get a color, it's our current color, and then we hit a repeat, and it just says the current byte just keeps cranking away. For int count equals 0, count less than run, plus count. Write the current to result. So I should get some of our bytes written out correctly. Really, it's the diff and the luma left. I think everything else is not too bad. Hey, C-Films. Glad to hear you're doing well. Good. We're doing good too. We're doing image compression with a QOI format. It's a one-page format. It's the top linked comment in the chat. One-page specification. We're trying it out. Right now we're looking at the different operations we can get per chunk. And I think opdiff is going to be not too bad. As we get delta red equals our byte and 110000. So that's hex 30. Red to green and blue. So that's hex C, 0C, and then it's probably 0, 3. Yeah. So red, green, blue. It's just a delta. So these are -2 to 1. So we have to this bit shifted or this bit shifted 2. This is not bit shifted. And the last piece is we have to subtract 2, right? Because it's 0, 1, 2, 3. Minus 2 gets me that -2 to 1 range. -2. So this is not going to be as robust or optimal of a compression as PNG, but it's a one-page spec, and it's the kind of thing you can read and understand, right? In one page, I kind of understand what's going on and how to do it. So our current color equals red of current plus dr bit shifted 24 pixels, or expecting a phone call, but I don't know, 954. I don't think that's what I need to worry about. Red, green, blue, 24, 16, 8. All right, I gotta take this just a moment. Okay, I'm back. Sorry about that. Got a couple of phone calls I'm expecting. Just gotta work them out here. So if I understand right, that's what this means. We're reading in, so this, each of these blocks matches a specific pattern of color usage in an image. This first one is, I have no reasonable prior thing in the image nearby to grab. So here's just the RGBA values. And if we're doing 3-channel, here's RGB. We're not going to use this one much. But maybe it's in the last few colors that we used, in which case, just give me an index into the previous colors. And this is a hash actually, but it's fine. But somebody tells me, here's the hash. As long as you've been keeping track of your colors the same way I am, we should have the same color in the array at the same point. So that's great. So it's a hash lookup, and it's literally like 3 multiplies. It's pretty small. This one says the two colors are very close, but slightly different. Like we're just varying a little bit from pixel to pixel. That's a very common thing. Nice smooth colors over a long range means with 1 byte, I can encode small changes in red, green, blue. Add those small differences, and then we throw it in the hash. So a lot of these involve us throwing things into the hash, into the array given the hash. That's to support this one. This one, I think, and we already discussed this a little bit, it's basically you are changing the brightness of the pixel, not the hue very much. So this pixel, this code would come in if you're changing the brightness and not the hue very much. There might be some hue shift, but not very much. This is due to like HSV, hue saturation value. You're changing the value, not the hue or saturation very much. So this is actually very useful for certain types of color patterns in an image. And then this one is run. Literally, it's the same color over and over again. Let's just run it out that many times. So, write out our current color to the result. So we have to figure out what we're doing here. Our result is like this, but we can treat it like pixel data equals result if we cast it as a color pointer. So really we're writing to pixels. So pixels at pixel index plus plus equals our current color. Plus plus column if column greater than width. Plus plus row. Column equals 0. So these are all things we'll end up having to pick up on here. We don't actually have to keep track of it in that way. We don't need to do this. This is the part that's left to do. Boom, there we go. I'm gonna take a quick restroom break. And then we'll do that Luma thing. Then we'll run a test against something. So I'll be back in just a minute. Okay, I'm back. Now, like I said, the Luma. So I'm just looking at the OK image format. We need to mask off 6 green bits, delta green. I don't think we actually use previous ever. It's always current. Whatever the current is updated. So I don't think we need previous in the decoder. Now, I'm looking at the Luma. Diff green is 1 byte. So we're going to get that. So delta green has no bias, I think. The green channel usually indicate the direction of change is encoded as 6 bits. The red and blue channels base their diffs off the green channel difference, which is a little bit weird, but RDG, I guess. Oh, we have to scan another byte though. We consumed all we need to there. We get another byte and we say int dr minus dg equals 4 bits of that and F0 downshifted 4 bits. We get those bits. Delta blue minus delta green is the lower 4 bits, like that. We don't really need to do this mask here. It's fine, it doesn't matter yet. We're not optimizing this stuff. Okay, so we have delta green dr minus dg, db minus dg. Which means
You can go to the
okay. I'm out of water, but we've only got like 45 minutes left of the stream anyway, so let's see. Current dr minus dg. Green shell difference from previous pixel minus 32 to positive 32. Minus 32. There's a positive 32 bias. Red channel difference minus green channel difference minus 8. I think that's correct. Current channel values are using your wraparound operation, so 10 minus 13, well, 250 plus 7 will wrap. Oh yeah, this is that wrapping thing. Same with the diff. I should pay attention to that. Okay, a bit of wrapping. Wrap. Same thing here in Luma. We have to wrap. But oh, I think we're not too far off. Oh, good heavens. This wrapping thing, it makes it a little bit more complicated. Do I want to write something more complicated? Let's work our way through the rest of this piece. This is where wrapping has to happen. These 3 bytes here. We're doing more bit shifting and masking than we really need to. We could do colors as a struct and a union. Or just a struct. We could do it as a struct. Maybe we just do a struct. Indentate TR GBA red green blue alpha. I want to make this a class. You can just wrap up the wrapping function in here. We need a destructor. It does nothing. Set R. If value is less than 0, are we overcomplicating our lives? Can't just take modulus, right? Let me think about modulus with negative numbers. Good night from you. All right, Drovest, you have a wonderful evening. Sleep well. See you tomorrow. Hopefully I've got this at least decoding tonight. Best way to test. Maybe we get a Python buffer up when we say negative, let's see here, -2 modulus 255. So it is just a modulus. And if we go to 67, no, 57 modulus 255, that brings it back down to 2. What were the examples he gave in that file? It's -10 minus 13, which is 253. So 10 minus 13 modulus 255 is 252. Oh, modulus 256. No, that's 253. And then 257. So 250 plus 7 modulus 256. Yeah, so this should work fine. The modulus 256 is the secret. Therefore, we don't have to do anything crazy. Yeah, let's just... Wrapping is easy. Modulus 256. 256. 256. And we do the same thing down here eventually. Current equals something like this. dr minus dg. So if I want the actual dr, I have to take dr minus dg and add dg to it. Int dr equals dr plus dg. I think that's all we can do there. Plus dg. So this would give us dr and db. dr, dg, db, same thing. We did the wrapping. Okay, so I think we've got everything. Now, at the end, we should assert. Uh-oh. Ooh, okay. Scan, oh. Okay. Finding color was not declared in this scope. We did two, oh. Color as unit 32T. Oh. FF was not declared. A was not declared. Agreed. No return. Alright, I think that's most of it. Now, unused variable. Yeah, we don't use previous actually ever. Raw. I'm fine with that. Delete raw as well. Okay. In theory, this is everything we need to run. So let's just try it. No warnings, good. It did things and I don't think it blew up. So echo $? Yeah, so it succeeded, whatever that means. Now, that doesn't mean that we've done it right. Are we actually doing the decode? We're doing the decode. The end of QOI, we should, assert that our pixel index is equal to width times height. And there it blows up. Okay. So it's not right yet. Okay, so if we have width, height, we get width times height. And is that equal to pixel index? 256 by 100, and that is not equal to that, and that is not equal to that. Well, there are several issues with this then. But we aren't really tracking it, so it's not the worst. I'm not surprised it's not working. I would like it to be a little closer than it is, though. QOI, not CPP. Oh, modulus X. Modulus D. 256 by 256. Is 65,536, which is correct. So these are expected. This is the unexpected. Insertion did indeed fail. So the question is, oh, pixel index plus plus. No, see, that should, every time we add something to the current pixel index, if we get this, we just increment once. If we get this, we increment once. If we get this, we increment once. Pixel index. Whatever we do to print it out is going to suck. Everything else is just one pixel. This is the only place where we can pick up extra pixels. I mean, I would expect several of these. Run of some number. I would expect any number of those within the example file I saw. Oh, interesting. Okay. This is not making sense.
Dad,
Hold on a second.
I have a bathroom.
Okay. How on earth is this not getting any runs at all? There are several times in the image I'm looking at where there should be long sequences of runs. E F F. Ooh. Offset equals 0. We read straight into current. Oh, here's a. Maybe I am being silly. Nope, nope, nope. I am not being silly. Okay. 1 byte, 1 byte, 2 bytes. Why oh why? RGBA, RGB. Which is fine. I'm not worried about that. Index. OP_diff. Oh, OP run. There's my problem. That's not the right code. I copy pasted too close to the sun. This is 1, 1, which is C. So we have 0, 0 for index, 0, 4, 0, 8. And I actually, not 0, 0, 0, 1, 1, 0, 1, 1. So this is 0, 0, 0, 1 is 4, 1, 0 is 8, 1, 1 is C. Okay. Whoops. Test file. Okay, all of a sudden that log statement looks like it's going to be a little silly. All right, success. I'll try a question mark. Now, I'm not saying it's correct, but a number of checks are passing. So the last piece of this puzzle, test QOI, is to write out a bitmap of this data with width and height, which we already kind of have in texture. So texture We're going to snag these three. Put those down here somewhere. We're going to snag this. And we're going to put it here. And we're going to clean things up a bit. We don't need that. File name. We do need a const char star. Something. Text. Oh, we can call it text. That's fine. Text, int width, int height. Okay, we'll even call them text width and text height. So we don't have to rename a bunch of stuff. And text. File name, fine, right? The could not open file, blah, blah, blah. Otherwise, header sizes, magic numbers. Right thing, so let's see here. Yep, these are the ones we're using. Red, blue, green channels. Color space doesn't really matter. Pixel data. Texture. Uint 8T. T text equals. It's probably not like something. Interesting. Okay, it doesn't fail. That doesn't mean it succeeds either. So we're going to put this in here somewhere. QBMP. This one. Right, bitmap. Label. So this needs the raw data, the width, and the height. Okay, then the MP. Crash. So if we run this thing, then in this folder, let's see, active projects, Sleuth. Run that. Open with GIMP. Shockingly. Okay, so let me show GIMP. All right, ready? Here we go. Here's GIMP. This is the input file. test card RGBA. And here's our output file, which is 100% wrong, but I've seen worse. Like, this is not unmitigated disaster territory yet. It should be similar. So yeah, not great, but it didn't blow up. I don't know what that means exactly. I don't know. Maybe red, green, blue come in a different order. Oh, we could actually test that. So let's go back. One time we do something a little bit different. Here is here. This. Here we scan current. So what if we say scan QOI B, get another byte, UNT alpha equals B, and this just becomes over alpha. Run this again. Reload this image. Same results. Let's pop that up. Not that one. Yep, there we are, right next to it. Like I said, not perfect yet. The fact that it's all grayscale makes me a little bit concerned. So let's go stare at our code a bit. Let's see if we can figure this out. We're going to consume a bunch of junk from 0 on. We're going to scan a byte. If that byte says this, we're going to scan the next 4 bytes and get red, green, blue, alpha. Shove those together. And red, green, blue, alpha. We're going to shove it into our array and shove it into our pixels. If we get an RGB, so if our current alpha equals our previous alpha, we can save ourselves a little bit. Okay. Actually, does it say in RGB what to do with that? Let me look at the spec again. The alpha value remains unchanged from the previous pixel, so that's correct. So we can save a byte every time we do different colors as long as the alpha is the same. Good to know. Index. We get the lower 6 bits. Get our current value. And dump it into our pixels. This diff should not be too hard. We get the current red, add the difference, bit shift and go. Shove it into the array, shove it into the pixels. Luma, I have the least faith in, but I would kind of expect something to work like our image to be a lot closer than this. QOIOP run. Well, maybe we do struct color uint 8t red green blue alpha. Zero, 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 1. 64 colors in an array. It says 0 fill, but I don't know that it matters. 0, 0, 0, 0? The specification says the running array, 0 initialized, is maintained by the encoder and decoder. Each pixel seen by the encoder and decoder is put into this array at the position formed by a hash of the color value. So our hash actually will change to c.r, c.g, c.b, c.a. Uint 8t opcode equals this. What the opcode is that? Code is that. Current red, current green. Actually, we can just scan it straight into here, huh? Current green, current blue. Let's just save ourselves some work here. Current is up to date. Green. blue. Current dot alpha. Nothing to do there. Scan, dump in the hash, dump it in the pixels. Otherwise, we get our opcode, get our current out of the array, and shove that all into this thing. Piece of cake. drdgdb current.read plus equals dr equals current.read plus dr modulus 265 red green blue. Don't do anything to alpha, and done. So we get our delta green, we scan another byte, get our delta red, delta blue, and current gets these things. Dump it in the array and the pixel hash. Run. Stuff the pixels clear full. I don't know if that would clean up anything. Oof. All right, well, we can write a hash. As a proper fraction function. Return c dot red, c dot green, c dot blue, c dot alpha, okay, 64. Okay. All right, open that file back up in GIMP and see if we're understanding the image correctly. So let me share GIMP, I guess. Here we are. So this is our previous attempt. Here's our newer attempt. This is the result we're looking for. I kind of expect the first instruction to come out of here is to write an alpha RGBA. Because this first pixel, top left corner. Is it possible I'm writing the bitmap out incorrectly? I suppose it's possible, but that code was working not too long ago. Red, green, blue, alpha, not a thing. Boolean swap. We don't need these. Yeah, none of our old data is using this. So let's see. Open up our file, binary, header size, etc., bit fields, width, height, interesting. How am I multiplying by 4 twice? Texture width times texture height is the number of pixels. Oh. Maybe. Red, green, RGBA. Red, green, blue, alpha. If I write them out in the expected order, I'm having an ordering issue here. Let's take that for a test drive. Open with GIMP. Well, we're getting color again. Let's see. Let's show that one. There we go. We've got a little color. But I now suspect, compared to this image, looks like this color. So it's getting smeared all over. Unless everything is completely endian swapped. Okay, it runs. We open with, yeah, not this one. Okay. And my colors are basically gone. Yep. Okay. Well. We're not as close as I'd like. How I choose to order this in memory doesn't matter too much. I could swear we have alpha. Color space sRGB. Oh. Isn't there something about alpha? I could swear. 1. Bitmap size, width and height in bytes. Width and height times 4. This has to be that, right? Yeah, we're just not getting there today, I guess. Show our latest and greatest. This is not exactly what I was hoping, but manually I should be able to check those colors against what's in the QOI. A couple of log statements. Therefore, I think we call it here tonight. We'll debug this tomorrow. I think we're close. We are processing every byte in the QOI data and getting the right number of pixels out while consuming all of the bytes. Therefore, I think we're walking it correctly. Let's make sure the instructions are correct. So tomorrow we'll take a look at that. We're gonna call it there tonight and get back to it tomorrow. So, yeah, I think we're close on this. Just trying to think if there's anything obvious I haven't looked at. Yeah, okay. So tomorrow, for sure, we're going to debug the QOI decoding, and then we'll work on the QOI encoding, which should be the opposite of this. And the only tricky part I have is, when do I use the Luma? And my guess is RGBA is the ultimate fall through, then RGB is the fall through before that, and then Luma is the fall through before that. And the others are used as efficiency requires. So I think we're good. You have a wonderful evening. We'll do this tomorrow, fix it up, and yeah, see you tomorrow. Bye-bye.